Hi everyone, I am Xiaoyu, a PhD student at Duke University. I'm going to talk about our work, Understanding the Security of Deepfake Detection. This is a joint work with my advisor, Gong. Deepfakes generally refer to forged media, such as images and videos. While forged media has been in existence for decades and was conventionally created by computer graphics methods, recent progress in deep learning enables automatic, large-scale creation of realistic-looking deepfakes. Many methods, such as generative adversarial networks, have been proposed to generate deepfakes, which we call deepfake generation methods. Such deepfakes can further be widely propagated on social medias to spread propaganda, disinformation, and fake news. As a result, deepfakes introduce grand challenges to the trust of online information. In our work, we focus on fake faces, major category of deepfakes, because faces are key components in human communications, and their forgeries lead to severe consequences. Due to the growing concerns of deepfakes, detecting deepfakes has attracted increasing attention from both academia and industry. A deepfake detection system includes two key components, that is, face extractor and face classifier. Given an image with human face in it, a face extractor locates and extracts the face region in that image. Then, a face classifier classifies the extracted face region to be real or fake. Different face classifiers are used. Roughly speaking, existing face classifiers can be grouped into two categories, that is, heuristic-based and neural network-based. Heuristic-based face classifiers rely on some heuristics to distinguish between fake faces and real ones. For instance, some researchers designed a face classifier based on the observation that the eyes in fake faces did not blink normally. However, such classifiers were easily broken by new deepfakes that fixed the abnormal eye blinking issue. Neural network-based face classifiers train deep neural networks to distinguish between fake faces and real ones. They achieve the state-of-the-art detection performance. However, existing studies focused on improving the performance under non-adversarial settings, while leaving the security in adversarial settings largely unexplored. For instance, a recent work showed that the face classifiers are vulnerable to adversarial examples. Here is an illustration. The face image is a synthesized one, and the face classifier can correctly classify it as a fake face. However, when we add some carefully crafted noise to it, the perturbed face image will be predicted as a real one by the face classifier. Despite that, it is hard for a human to tell the difference between the face on the left and the face on the right. In this work, we perform systematic measurement studies to understand the security of deepfake detection. The security of a deepfake detection method relies on the security of both the face extractor and the face classifier. Therefore, we perform measurement studies to understand the security of both components. In particular, we aim to study the following three questions, where the first question is related to the security of face extractor, while the other two questions are related to the security of face classifiers. Specifically, we notice that an attacker can easily add perturbations, for example, Gaussian noise, to his deepfake images. Therefore, our first question we aim to study is, can a face extractor still successfully extract the face region if an attacker adds small perturbation to it? Moreover, we observe that existing studies often train and test a face classifier using fake faces that are generated by the same deepfake generation methods. However, many different methods have been proposed to generate deepfakes, and new methods are continuously developed. Therefore, the second question we aim to study is, can a face classifier trained using fake faces generated by some deepfake generation methods correctly classify fake faces generated by a different method? And also, a face classifier is a binary machine learning classifier. The adversarial machine learning community has developed adversarial examples and data poisoning attacks for machine learning classifiers, which attack classifiers at testing phase and training phase respectively. Recent studies showed that a face classifier is vulnerable to adversarial examples. The third question we aim to study is, are these face classifiers also vulnerable to data poisoning attacks? Next, I will first introduce our measurement setup. We extract 6 face image datasets from 2 large-scale public sources, that is, Face Forensics++ and Facebook Deepfake Detection Challenge. Specifically, we use the open-source dlib package to extract the face images in each frame of Face Forensics++ videos and group them based on the deepfakes generation methods. As a result, we obtain F2F, NT, FS, and DF datasets. We use the same face extractor to extract the face images in the frames of Facebook Deepfake Detection Challenger videos, and we obtain the DFDC dataset. We further consider a dataset that is a combination of these 5 image datasets, which we call the all dataset. We split each of the 6 image datasets into 72% training data, 14% validation data, and 14% test data. We train exception neural networks as our face classifiers following the Face Forensics++ work. We initialize the model with the pre-trained weights on ImageNet and replace the last layer with the fully connected layer with 2 neurons. We train the model with the training dataset and choose the best model during training with the highest validation accuracy. We will evaluate the face classifier using 3 metrics. The first one is accuracy. The accuracy of a face classifier is defined as the fraction of the test face images that are correctly classified by the face classifier. Accuracy is an aggregated metric, which does not distinguish the detection performance of the real faces and fake ones. Therefore, we further consider true positive rate and true negative rate. The true positive rate of a face classifier is defined as the fraction of fake faces that are correctly classified as fake by the face classifier. When an attacker tries to evade detection, its goal is to downgrade the true positive rate. The true negative rate of a face classifier is defined as the fraction of real face images that are correctly classified as real by the face classifier. After introducing our measurement setup, now let's look at our first question. Is face extractor robust to Gaussian noise? Note that the security of a deepfake detection system relies on the security of both face extractor and face classifier. For example, if the face region cannot be extracted accurately from an image, deepfake detection fails. We know that when fake faces are fed into the face extractor, the face extractor will locate the face region and extract it. However, what would happen when we add Gaussian noise to the fake faces before parsing them to the face extractor? Can the face extractor still successfully extract the face region? Recall that each of our datasets includes face images obtained from deepfake videos. We added random Gaussian noise with mean 0 and standard deviation sigma to each of the 3 RGB channels of each pixel in an image frame. Then we use dlib package to extract the face region in the noisy image frame. We define the face extraction success rate as the fraction of the face image frames in the dataset for which dlib successfully extract the face region. This figure shows the face extraction success rates with respect to the standard deviation sigma. We observe that when the noise level sigma is small, the dlib face extractor can extract the faces in most image frames. However, when sigma increases, the success rate drops quickly, indicating that the face extractor fails to extract the faces when a relatively large Gaussian noise is added to the image frames. For example, when sigma equals to 0.4. This figure shows a pair of example image frames without and with Gaussian noise. We observe that human can hardly notice the noise even if sigma is 0.4. Our results imply that an attacker can evade detection via simply adding random Gaussian noise to evade a face extractor. Next, we come to our second question. Can face classifiers generalize well? To answer this question, we studied the cross-method generalization of face classifiers. Specifically, we trained the face classifier with fake faces generated by Deepfake's generation method M1, and then we test this face classifier with fake faces generated by another method M2. In our experiments, we select one method from F2F, NT, FS, and DF as M1, and one method as M2. This table shows the true positive rates of the face classifier. The rows represent the M1 we use to train the face classifier, and the columns represent the M2 we use to test the face classifier. We observe that the diagonal values in the table are large. This means that a face classifier trained on Deepfake's method M1 can accurately detect the deepfakes generated by the same method M1. However, the off-diagonal true positive rates are close to 0 in many cases, which means that a face classifier classifies almost all test fake faces generated by a different method M2 as real. This indicates that a face classifier trained on deepfakes generated by some method cannot detect fake faces generated by other methods. Our results imply that an attacker can evade detection via generating deepfakes using a new deepfake generation method. Now, let's consider our third question. Are face classifiers vulnerable to poisoning attacks? To answer this question, we consider two different data poisoning attacks. The first one is label flipping attack, which flips a fraction of labels in the training dataset from fake to real or vice versa. The other one is backdoor attack, which aims to poison the training examples such that the corrupted classifier predicts any test face image with the trigger embedded as a real face. To perform the backdoor attack, we randomly select a fraction of training face images, embed a chessboard-grade trigger to the image, to the bottom right corner of them, and set their labels to be real. The actual size of the trigger is very small compared to the face images. That is, the trigger size is only 0.1% of the image size. Here we use a large trigger to highlight it. We perform the experiments on the all dataset. We evaluate the attacks with different fraction of poison data. The figure on the left shows the results for label flipping attacks, and the figure on the right shows the results for backdoor attacks. We observe that the face classifier can resist a large fraction of flipped labels in label flipping attacks. For instance, when 40% labels are flipped, the face classifier can still achieve high accuracy, true positive rate, and true negative rate. However, when only 5% of training faces are embedded with a trigger, the true positive rate drops to 0 in backdoor attacks, which indicates that the face classifier classifies all test faces with the trigger as real. Our results show that an attacker can evade detection via backdoor attack that only poisons a small fraction of training data. To conclude, our extensive measurement shows that existing deepfake detection methods are not secure, despite their reported high accuracy, which highlights that the major challenge of deepfake detection is to enhance its security in adversarial settings. Thank you for your attention.